You know what really gets me? When light leaves a star 1 billion light years away and travels for 1 billion years to reach your eye from the light's perspective. No time passes at all. Zero. Nothing. 1 billion year journey that takes no time whatsoever. And this isn't poetry, this is physics. By the time we're done here, you'll understand exactly why this happens, deep in your bones. Let's start simple. What's time? You say it's what clocks measure. Fine. But what do clocks really do? A clock is just something that repeats. A pendulum swings, a crystal vibrates, an atom oscillates. We count the repetitions and call that time. So time is really about processes happening inside things. Your clock defines your time. Here's where it gets strange. You and I have identical clocks, standing next to each other, ticking together. 1 second for you, 1 second for me. Perfect agreement. Now you get on a rocket and fly away very fast. What happens to your clock? You'd say nothing happens. It's the same clock, ticks the same rate. And from your perspective, that's absolutely true. But from my perspective, watching you zoom away, your clock runs slow. Not because it's broken, but because of the nature of space-time itself. And this is real. If you fly away fast and come back, we compare clocks. Yours will have ticked fewer times. Less time will have passed for you. We've tested this with atomic clocks on airplanes. It's a fact. Time is not absolute. Time depends on how you're moving. The faster you move relative to me, the slower your time runs. This is time dilation. Why should motion affect time? What's the connection? This is where Einstein comes in. And it starts with light. Light is strange. If I throw a ball at 10 miles an hour while standing still, then throw it from a train moving 50 miles an hour, the ball goes faster. Speeds add up. But light doesn't work that way. I shine a flashlight standing still, light goes at the speed of light. Call it C, about 186,000 miles per second. Now I get on a rocket going half the speed of light and shine the same flashlight forward. You'd expect the light to go at 1.5 times C, my speed plus the light's speed. But it doesn't. The light still goes exactly at C. Not faster, not slower, exactly C. This was discovered experimentally, and it was confusing as hell. How can light always go the same speed no matter how fast the source is moving? Einstein realized the only way this makes sense is if space and time themselves are different from what we thought. If the speed of light is truly constant for everyone, something else has to give. And what gives is our notion of absolute time. We naturally think of time as a river flowing at the same rate everywhere. 1 second is 1 second everywhere for everyone. But that can't be true if light always goes at C. The math forces you to conclude that time flows at different rates for different observers. The key factor is velocity. The faster you move, the slower your time runs relative to someone at rest. Let me give you an analogy. Imagine walking across a field. You can walk north, east, or somewhere in between. You have a fixed walking speed, say 1 mile per hour. Walk purely north, you cover 1 mile north in an hour. Walk purely east, 1 mile east. But walk northeast, you cover less than 1 mile north and less than 1 mile east because your motion is divided. Space-time works the same way. Everything moves through space-time at the same total rate. We call this the cosmic speed limit, and it's exactly the speed of light. If you're sitting still in space, all your motion through space-time goes into time. You move through time at maximum rate, 1 second per second. But start moving through space. Some of your space-time motion gets redirected from time into space. You move through time slower. Your clock ticks slower. The faster you move through space, the more of your space-time motion goes into space and less goes into time. Your clock slows down more and more. Here's the punchline. What happens when you move through space at the speed of light? Then all your motion through space-time goes into space. Nothing left for time. Your clock stops completely. Time doesn't pass at all. This is why time stops for light. Light moves through space at maximum possible speed. It uses up all its motion through space-time just traveling through space. Nothing left for time. Let me say that again because it's crucial. Everything moves through space-time at the same total rate, the speed of light. Use all that motion for traveling through space. You have none left for traveling through time. That's what light does. That's why time stops for light. Think of it like a highway with a speed limit of 100 miles per hour. Drive north at 100. You make no eastward progress. Drive east at 100. No northward progress. Drive northeast at 100. You make progress both ways but less than 100 in each. Space-time is like that highway. Your speed through space-time is fixed at C. Use all that speed traveling through space. You have no speed left for time. Time stops. Now be careful here. When I say time stops for light, what do I mean? Does light experience anything? Does a photon have a point of view? Photons aren't little people. They don't have experiences like we do. When I say time stops for light, I mean something specific and physical. If you calculate what a clock would read traveling at light speed, the answer is it wouldn't tick at all. No time would pass on that clock. We can't actually build a clock that travels at light speed, because clocks are made of matter, and matter can't reach light speed. Only massless things like photons can travel at c, but we can take the limit. Ask what happens as you go faster and faster, closer to light speed. Time slows down more and more, and in the limit, time stops. So when a photon is emitted from a distant star and travels 1 billion years to reach your eye, from the photon's perspective, there's no journey. The emission and absorption happen at the same instant. The whole trip takes 0 time. This sounds like poetry, but it's hard physics. Falls directly out of the equations of special relativity. No way around it. Let me make sure this is clear. Everything in the universe is always moving through space and time together. Think of having a limited budget. You have a fixed amount of motion to spend. Spend it on moving through space or moving through time, but not both fully at once. Sit still, not moving through space. All your motion goes into time. Time passes at normal rate. Start moving through space. You use some motion on space, so you have less left for time. Time passes slower for you. Light moves through space as fast as anything can possibly move. Uses up all its motion budget on space. Nothing left for time. Time doesn't pass for light at all. People sometimes think time dilation is just about appearances. It just looks like the clock runs slow, but really it's normal. Wrong. Time dilation is not an optical illusion. It's a real physical effect. 2 twins separate. One travels at high speed, the other stays home. When they reunite, the traveling twin will be younger, actually physically younger. Fewer heartbeats, fewer thoughts, fewer birthdays. This is real. The confusion comes because we think of time as absolute. We think there's some universal clock ticking away, and everyone's local clock tracks that universal time. But there's no universal clock, no background time. Time is local. Every object has its own time, determined by its own history of motion. This is hard to accept because it's so different from everyday experience. But everyday experience is limited to low speeds. We never move fast enough to notice time dilation. Fly in an airplane, time dilation is real but tiny, billionths of a second. Can't feel it, but it's there. At speeds close to light, time dilation becomes huge. At 90% of light speed, time runs at about half rate. At 99%, about a seventh. At 99.9%, about a 20th. As you approach light speed, time slows to a crawl, then stops entirely. Another thing people get wrong, they think there's something special about light itself that makes time stop. Light has some magic property that freezes time. Not quite right. What's special is the speed. The speed of light is the cosmic speed limit, the maximum speed anything can travel through space. And it's the total speed everything travels through space-time. Light travels at this speed through space because light has no mass. Anything without mass must travel at exactly this speed. Can't go slower. If there were other massless particles, they'd also travel at c, and time would stop for them too. In fact, there probably are. Gluons that hold quarks together are massless. They travel at c. Time stops for them. Gravitational waves, ripples in space-time itself also travel at c. Time stops for them too. So it's not about light specifically. It's about the speed. The speed of light is special because it's the structure of space-time itself, built into the fabric of the universe. Let me walk you through a thought experiment. Imagine a very simple clock, a light clock. 2 mirrors, one above the other, separated by 1 meter. A pulse of light bounces up and down between the mirrors. Each time it completes a round trip, the clock ticks. This clock is sitting still in my lab. Light goes straight up, hits the top mirror. Comes straight down, hits the bottom mirror. Tick. Time for 1 tick is the round trip distance divided by speed of light. 2 meters divided by c. Very fast ticks, but it's a clock. Now put this clock on a rocket that zooms past me at half the speed of light. What do I see? The clock is moving horizontally. The light pulse goes up. But while it's going up, the clock moves to the side. So the light doesn't go straight up. It goes diagonally up and to the side. Then comes back down, also diagonally. Here's the key. The light still travels at c. Speed of light is the same for everyone. So the light travels diagonally at c, but the diagonal path is longer than the straight path. It takes longer for the light to complete the round trip. See what happened? From my perspective, watching your moving clock, the clock ticks slower. The same pulse takes longer because it has a longer path to travel. And this isn't some trick of the light clock. Any clock would slow down the same way because all physical processes depend on the structure of space-time. And That structure says moving clocks run slow. You might ask, what about from your perspective on the rocket? From your view, you're sitting still and I'm the one moving. Do you see my clock running slow? Yes. This is the weird part. From your view, you're at rest. Your clock ticks normally. But you see my clock moving relative to you, running slow. Each observer sees the other's clock running slow. Seems like a contradiction, but it's not. The resolution comes when you try to compare clocks directly, and that involves acceleration, which gets complicated. But here's the key. If you keep moving at constant speed forever, you and I each see the other's clock running slow. No paradox. The paradox only seems to arise if we bring the clocks together to compare directly. When we do that, one of us has to accelerate, and that breaks the symmetry. Take this further. You're on a spaceship traveling at 99% light speed. What's time like for you? From your perspective, everything's normal. You're just sitting there. Your heart beats normally. You breathe normally. You think normally. You don't feel like anything weird is happening. But from Earth's perspective, you're moving incredibly fast, and your time is running at about a seventh the rate of our time. You age 7 times slower than we do. So you could travel to a star 10 light years away. From Earth's perspective, the trip takes 10 years at close to light speed. But from your perspective, because your time runs slower, the trip might take only a year or so. You experience less time. And here's the really strange part. From your perspective, it's not just that time passes slower. The distance to the star actually appears shorter. This is called length contraction. Space and time are connected. When time changes, space changes too. At light speed, this goes to the extreme. From the photon's perspective, if we could say such a thing, the distance to its destination is 0, and the time to get there is 0. The entire universe along the direction of travel is compressed to a single point. The departure and arrival happen simultaneously. There's no journey at all from the photon's frame of reference. Now here's what Feynman would love about this. All these strange effects, time dilation, length contraction, the speed of light being constant, they all come from one simple fact. The laws of physics are the same for everyone. Doesn't matter if you're standing still or moving at constant velocity. The laws work the same way. Einstein called this the principle of relativity. And once you combine this with the experimental fact that light travels at the same speed for everyone, everything else follows inevitably. You don't need to imagine curved space-time or extra dimensions or any fancy stuff. Just those two simple principles. Laws of physics are the same for everyone, and light speed is constant. From those two facts, you can derive time dilation, length contraction, all of it. The math isn't even that hard. It's mostly just algebra and the Pythagorean theorem. What's hard is accepting the conclusion because it's so different from everyday intuition. But nature doesn't care about our intuition. Nature is what it is. And what experiments tell us over and over is that this is how the universe works. Time is not absolute. Space is not absolute. What's absolute is the speed of light and the laws of physics. Everything else is relative, depends on how you're moving. This is the core insight of relativity. So when you look up at the night sky and see starlight that's been traveling for millions or billions of years, remember that from the light's perspective, no time has passed. The photon that hits your eye right now from its own frame of reference was just emitted. The star in your eye exists at the same moment in the photon's experience of reality. The vast cosmic distances that separate us become nothing light's point of view. And this tells us something profound about the nature of reality. Our everyday experience of space and time is separate. Fixed things is just an approximation. It works fine at low speeds, but it's not the deep truth. The deep truth is that space and time are unified into space-time. And the way you move through space affects how you move through time. They're not separate. They're two aspects of the same thing. Mass and energy work the same way. They're not separate. They're unified by Einstein's famous equation, E equals mc squared. Matter is just concentrated energy. Energy is just spread out matter. The speed of light squared is the conversion factor. And that same speed, c, is the cosmic speed limit, the speed at which causality propagates, the speed that defines the structure of space-time itself. Everything connects. The reason you can't go faster than light isn't because engines aren't powerful enough. It's because going faster than light would mean going backward in time, violating causality, creating paradoxes. The universe doesn't allow it. The speed of light is absolute, not as some arbitrary limit, but as a fundamental feature of how cause and effect work. And for light itself, traveling at this cosmic speed limit, time stops. Not metaphorically, not approximately, but exactly and completely. The journey across the universe takes no time at all from the photon's perspective. That's not mystical. That's just what the equations tell us. And those equations have been tested and confirmed in every experiment we've ever done at high speeds. So the next time you see sunlight, remember that from the photon's perspective, it was just emitted from the sun's core. It didn't travel for 8 minutes from the sun to Earth. Those 8 minutes are our experience, not the photons. The photon exists outside of time, in a sense. It connects the moment of emission to the moment of absorption directly, with no time in between. That's the nature of light. That's the nature of space-time. That's how the universe actually works. And once you understand this, really understand it, you can't see the world the same way again. Time isn't what you thought it was. Space isn't what you thought it was. They're flexible, they're relative, they depend on motion. What's absolute is the structure that connects them. Space-time itself, governed by that one universal speed, the speed of light. And at that speed, time stops. That's not a bug, that's a feature. That's how reality is built down at its foundations. And that's beautiful.